Bismillahir Rahmanir Rahim. This is our 12th episode. It's going to be about the limiting reactants. Actually, here, as usual, this is the syllabus of the chapter 5, and we are going to go through all of it. So don't worry, we are doing well till now, and we will finish it. I'm not going to stand here for a long period of time telling you the same thing that I have told you before. So you just go through those items and you will know what you should have in this part of or this chapter, especially in this chapter. There is a little differences I would like you to understand or to observe. If you see here the number here is 3.3. It is not about chapter 3. This is about chapter 5, because when they make the curriculum, this should be with chapter 3, but now they are split it into sub chapters. So now we will work in chapter 5, not in chapter 3. So let us go and see what is going on, and you can revise each one of these and know that this part is for the core students, while this one plus those 8 items are for the supplement. Limiting reactants. Let us avoid speaking in chemistry or just telling you a chemistry language. Let me try to go or emerge out of or exit from the chemistry towards the daily life. Assume that you would like to make a recipe of something. You want to have a food, for example, and you want to make recipe for this food. You know the recipe and you know the ingredients that you are going to use, and you know the amounts of them, regardless of what this recipe is. Let us assume it is composed of only 2 items, item A and item B. So you want to make this recipe for 1 person. For example, let us take the front example here. You want to make a recipe, and this recipe has 2 ingredients, this one and this one. And you are going, when you make your recipe, it's going to give you this shape. So this is your recipe, and then there are going to be some remaining items here. Now, if the recipe could be formed with 2 ingredients, 2 of these items, 2 units of these items, plus 1 unit of this item, there will not be any problem, because your recipe is going to be made by using 1 of this item, though that this item have more units, and those 2 items which are here, and you are going to make your recipe, which is A to P, and then the remaining of the B is going to be here. Till now, there is no problem. When the problem comes, if you want to make for more than 1 person, let us assume 3 or 4 persons. So you need more units of this, because 2 units of this plus 1 unit of this is going to make your recipe. Otherwise, it's not going to be used. You have to cut this into 2 pieces for to give it to 2. However, if you want to make recipe for each of the 2 persons, you need 4 units of this. And you need 2 units of this. Although, despite of this one is 5 units, have 5 units, and those 5 units are more than enough because you are going to use 1 unit in each recipe. Okay? But what you can do for this is only for one recipe. When for example, 1 dish. You can't make 2 dishes from this. 2 bowls. You can't do that. You have to do, in order to do 2 dishes, you need 4 items of this. So this is because it is few. It is little. It is a smaller amount. And this is more than enough. That means it is in huge amount compared to this. This item is called a limiting item or a limiting recipe item, because if this is not 4, you cannot make 2 dishes. Still, despite of those are 5 and you have enough. So this is called a limiting recipe factor, while this one is an excess recipe factor, because you are going to exhaust all these items. However, still there is some from here. So if I have an atom or 2 elements, for example, element A and element B, and I need 2 atoms of element A to react with 1 atom of B to make A2B compound, the A atom is called limiting element or limiting reactant, because it is gonna be consumed all while still there is an excess of this. So in any chemical reaction, you are going to find 3 levels. Either you have a limiting reactant, that means you have one of your elements or compounds that are very few or little or smaller in amount, and it cannot be you cannot exhaust more than what you have, and this is called a limiting reactant, because when it is finished the reaction is going to stop. On the other hand, you are going to see a compound or an element like this one, which is in excess, in abundance. It is a greater amount, and it is more than enough, more than needed to do the reaction, and this is called the reactant in excess or the abundant compound, or when we say that it is enough to do something, so it is here, and this is your compound. If you consume all this limiting element or compound, the remaining of this are called the remaining of the excess compound. So this is simply what is meant by limiting reactants. A limiting reactant is the reactant that is not in excess. It is to say, of a smaller number of moles among other reactants. Okay, if we consider it in moles. Now you can say here, okay, this is 2 moles, but this one is 1 mole. How it is in an excess, and this is the limiting factor? Because the units here are more. I don't need but 1 mole, but here I need 2 moles. If I consume those 2 moles, then the reaction is going to stop. There is no more reaction. The reaction is no longer going on. It's going to stop. On the other hand, we can see that an excess reactant is the reactant that is in excess or in a greater amount. It is to say in a greater number of moles among other reactants. Some of these moles I don't need it in the reactant because they are more than enough. Now we have an opportunity to understand what is going on. Let us go and see what else we have. Let us try an example to understand how we can make a chemical recipe in order of making a food recipe. So our example says 6 grams of coupled 2 carbonate, reacted with 0.08 mole of hydrochloric acid to produce copal 2 chloride show that the coupled 2 carbonate was in excess. Now let us first recall our statement that says understanding the question or the problem is halfway to it is solution, or it is way of solving it. Now what I have is 6 grams of coupled 2 carbonate, which was reacted with 0.08 mole, but not gram, of hydrochloric acid. So I have 2 reactants, but I have them in different measurements. One in grams, the other one in moles. The third thing is, what is the question? What is the problem asked about? They say that show that the coupled 2 carbonate was in excess. That is to say, in other words, proof that coupled 2 carbonate is an excess reactant. So we have to go one by one to see what is going on. Now, first I have to write proper balanced equation, which says coupled second carbohydrate, coupled 2 carbohydrate, carbonate, not carbohydrate, carbonate plus HCl, which is hydrochloric acid, gives coupled 2 chloride plus water plus carbon dioxide. So this is a proper, and just by adding 2 to copper 2 chloride multiplied by 2, that means we have 2 moles of copper chloride. Now it is a proper and balanced equation. Step 2, to determine the relative molecular mass of coupled 2 carbonate, and it is from here. I just bring all these items in order you can understand which one is that. So it is coupled sorry, here. It's coupled, which is coupled, that is a relative atomic mass is 59, and 12, which is a relative atomic mass of carbon, and 3 multiplied by 16, which is the relative atomic mass of oxygen. When we add this, make the mass and add this together, it's going to be 119 gram per mole, which is the molecular mass of the, or the relative molecular mass of coupled 2 carbonate. Now, when I finish this, I have to determine, using the information that have been supplied to in the problem, I have to determine the number of moles of coupled 2 carbonate. What I have is that I have 6 grams of coupled. So I have the mass, 6 gram of coupled, and also I have the number of moles. So I have I have the molar mass, which is 119 gram per mole. I calculate this. So by dividing this and using this equation, which says the number of moles equal the mass in gram over the molar mass, I'm going to have it like this, that the number of moles of coupled 2 carbonate equals 6 over 119, which is 0.05. Simply mole of. So now I determine how many moles are found in 6 grams of coupled. Okay? Now, we are going to shift to the other scene where we are going to use step 4. So be careful when we move there. Now, in step 4, I want you to try to understand this step one by one. So we have the balanced equation. You know it. We already talked about it. And then from here, we are going to bring or pick up some information. It says that 1 mole of copper 2 carbonate reacts with 2 moles of hydrochloric acid. So the mole ratio is 1 to 2. If I have 1 mole of copper 2 carbonate, this 1 mole is going to or will react with 2 moles of hydrochloric acid. So if I don't have the 1 mole, I have less. If I have 0.05 mole of carbon 2 carbonate, how it's going to react? How much or how many moles of hydrochloric acid is going to be used? It is simple. If 1 react with 2, then 5 react with 10, then 50 react with 100. So you are going to multiply the number of moles of copper carbonate by 2. You are going to have the moles required for the hydrogen. So if I have 0.05 moles of carbon of coupled 2 carbonate, this will react or will be enough to react with 0.1 mole of hydrochloric acid. But what we have here, we don't have 0.1. We have less than 1.1. We have 0.08 mole of hydrochloric acid. So since 0.808 moles of hydrochloric acid, which is the reactant, and this is given, is less than 1 mole of HCl, that means the HCl is a limiting reactant. The HCl is a limiting reactant. And if the HCl is a limiting reactant, that means that the carbon, the coupled carbonate is in excess, is an in excess reactant. We can use, I'm going to leave this for you. We can use this in different ways. That in doing this with coupled, we can do it with HCl and come to the same conclusion. And I'm going to leave this for you to do it. Don't use the coupled two carbonate, but use the hydrochloric acid, the information of hydrochloric acid. I'm sure that you are going to reach the same process or reach the same results, and then you send it to me in the comment down, and I will see it and see if it is correct or not. Now, the second example is very easy. It is very easy, and we are going to apply everything one by one to it. Now, the second example says that 4 grams of magnesium is reacted with a hydrochloric acid solution that contains 5.48 grams of acid. And he gave us the type of the equation and balance equation. Magnesium, this is a solid. S stand for solid, and here hydrochloric acid, aqueous solution, that means it is a solution or liquid. Magnesium chloride is aqueous solution, and H2, which is a gas. Now we are going to deal with the same. I'm going to leave this out, to take those information out and put it as it is, as usual. So as usual, we are going to determine that 1 mole of magnesium is going to react with 2 moles of hydrochloric acid to give us those ones. And the same thing, I'm going to do these calculations to determine the AR of magnesium and the molecular MR of HCl. AR of magnesium, I get it from here, which is 24, and the MR of this, I'm going to add all of these together. So it is HCl, that means 1 hydrogen plus multiplied by 1, which is the AR of the hydrogen, and then 1 atom multiplied by AR of chlor, which is 35.5%. And when we add them together, it's going to be 36.5. Now, after that, I'm going to determine the number of moles for the magnesium and also for the hydrochloric acid, using the formula that we know, that the number of moles equal the mass in grams over the molar mass in gram per mole. Now, for the magnesium, I have 4 grams of magnesium. So 4 grams of magnesium over 24 equal 0.17 gram of gram per mole. Actually, yes, gram per, no, it is just mole. It's not gram per mole, it is mole. This is the number of moles that I want. And this is here, the number of moles here are also 15, 0.15. That means I have to divide 5.48, I bring it from here, over the 36, which is the one that I calculated for it, the molecular, and that is going to be 0.15 mole. So now I know how many moles are here, as he said to me. It is 0.17 mole for the magnesium and 0.15 mole for the HCl, or the hydrochloric acid. Let us go further and see what's. Now is the second scene, or the other portion of the problem. The other portion of the problem is to determine which of the reactants is the limiting reactant. We have two reactants here, and we need to know which one is which one is the limiting one. If you know the limiting one, then you perceive, or obvious, you are gonna know which one is in excess, because the other one is gonna be in excess. Now let us go one by one. So from our balanced equation, we are gonna come out with this information that 1 mole of magnesium reacts with 2 moles of hydrogen chloride, and this means that the mole ratio between the two reactants is 1:2. Now we already have 1.7 mole of magnesium would react. So based on this, if I have 1.7 mole of magnesium, based on what we have here in our calculation in the first scene, that means we must have 3.4 mole of hydrogen chloride. In order to react completely with this, we need 3.4 of HCl. But, or since we have only 0.15 mole of HCl, which is more or less than the 3.4 moles of HCl, that means the HCl is the limiting reactant, because the amount present in the actual experiment, or the actual reaction, is less the amount of moles, the number of moles, how many moles present in the actual life is 0.15 or 0.15 mole. In order for the 1.7 that we have, 1.7 mole of magnesium present in ours, we need, for all this magnesium to be exhausted, we need 3.4 mole of hydrogen chloride, but we don't have this. We have limited amount. So HCl is the limiting reactant. On the other hand, if we reverse it, we are gonna prove that magnesium is the reactant in excess, the reactants in abundance, the reactants who have greater number of moles. Very easy, simple. Let us take a third example in order to elaborate the concept of limiting reactants and excess reactants. Now, it is a little bit different, not too much different, but a little bit different. And here we are going to widen your horizon of solving problems. So what is the problem is? The problem says, or the example says, what is the maximum amount of ammonia gas produced in moles, so I want it in moles, that would be produced by the reaction of 4.5 moles of nitrogen and 12 moles of hydrogen. Determine the limiting and the excess reactions and the remaining amount of moles left. So we are going here to do a lot of things, and we have to be careful of doing it. So he wants the maximum amount of ammonia gas produced. So he wants the product, the maximum amount of the product. Second, the maximum amount of the product produced when we burn 4.5 moles of nitrogen and 12 moles of hydrogen. This is the first part. The second part is to determine the limiting and the excess reactants and the remaining amount of moles left. Let us go one by one and see what we should do. In step one, as usual, you are going to go through it and make a proper equation that says a molecule of 1 mole of nitrogen with 3 moles of hydrogen is going to give you 2 moles of nitrogen. And in step 2, you are going to, based on this information, to come out with that you need 1 mole of nitrogen, 3 moles of hydrogen to produce 2 mole of nitrogen, ammonia gas, which is important. So it is 1 to 3 if we are talking about nitrogen and the ammonia, or 3 to 2 if we are going to talk about the hydrogen and ammonia, or 1 to 3 if we are going to talk about nitrogen and hydrogen. So let us go one by one and see how we are going to solve this problem. We have a statement saying that understanding what is the problem, it is a halfway of its solution. So let us go again to the problem or the example and see what they need actually, what they are asking about. So it says what is the maximum amount of ammonia gas. So he needs to know one of the demands or one of the items that he wants us to answer it is what is the maximum amount of ammonia gas. I'm going to put this in, just put this in the back of your mind, and I am going to ask you to solve this part, but I'm going to help you in doing the other parts. This is the first one. The second one is that we have an information that 4.5 moles of nitrogen reacts with 12 moles. What we have is 4.5 moles of nitrogen and 12 moles of hydrogen. we need to determine, second, because first is the maximum amount, second is determining the limiting factor or the limiting reactant and the reactant in excess, and also the remaining amount left. Okay, let us go one by one. In order to do that, we are going to squeeze our information in a way that part of the information will confirm the other part of the information. We're going to solve it with one strategy, then we use the second strategy in order to confirm our first strategy. Let us go for this. Now, first of all, let us start with nitrogen and just forget about the others. So if I have the nitrogen, and from my equation, the mole ratio is 1 to 3, 1 mole of nitrogen and 3 moles of hydrogen. This is going to be 1 to 3 equation, 1 to 3 relationship. From the above, we have 4 point, but we don't have 1 to 3, we have 4.5 moles of nitrogen. So this 4.5 moles needs to react completely with 4.5 multiplied by 3 over 1 equal 13.5 moles of hydrogen. But before I proceed, I would like you to tell me in the comment section from where I get this information, 4.5 multiplied by 3 over 1, which equal to 13.5 moles of hydrogen. Now, this is the first result by using nitrogen. So in order to completely have the nitrogen reacted, the 4.5 moles completely react with hydrogen, it needs 13.5 moles of hydrogen. However, in the same problem, I just have 12 moles of hydrogen. I don't have 13.5 moles. So 12 moles is less than the 13.5. As a result, if we start the reaction, the nitrogen, the hydrogen is going to be consumed before all nitrogen is going to consumed. And from here, hydrogen is the limiting factor, is the limiting reactant, because the reaction is going to stop after we consume the whole 12 moles of hydrogen, and still we need more still we need more hydrogen to be consumed, and there is also still more nitrogen present. Now, okay, this is the first portion. I would like to use another strategy to confirm my result of the first strategy. Let me start with hydrogen, not nitrogen. So based on the information, which is the mole ratio is 1 to 3, I have 12 moles of hydrogen that reacts with 12 multiplied by 1 over 3 equal 4 mole of nitrogen. So the 12 moles of hydrogen, in order to be completely react, it needs just 4 moles of nitrogen. Now, when you go back to the test here or to the example, you are going to see that the given amount of nitrogen is 4.5 moles. So 4.5 moles of nitrogen is given to us, which is more than the 4 moles needed by the 12 moles of hydrogen. This means that nitrogen is a reactant in excess because it is going to remain although all the hydrogen is consumed. And if we need the remaining one, it's going to be 4.5, which is the nitrogen. The only one is going to remain. We consume 4 by the 12. And this is 0.5 mole of nitrogen. So this strategy is telling us that nitrogen is an excess amount. And in the first strategy, tell us when we use nitrogen, tell us that hydrogen is the limiting reactant. So now we solve 3 parts of the problem, 3 out of 4. We know that the hydrogen is the limiting reactant. We know that the nitrogen is the reactant in excess. And we also know that the remaining amount of nitrogen is 0.5 mole. Now, what is left is to determine the maximum amount of ammonia gas, and I'm going to let you know, tell me how much is this amount, how many moles of ammonia gas is produced by using completely those two. So we are going to use 4 moles of nitrogen in addition to 12 mole of hydrogen. How much they are going to give us moles per moles? Please be careful. Now we finish this. I want you to give me this answer down in the section, in the comment section. Don't forget to do that. Thank you. Let us go forward. Now we finished an important topic, the limiting factor. We solve 3 examples. We have 3 examples of this in addition to the illustration example, so you can easily understand what's meant by the reactant in excess and also the limiting reactants. Also, you can get the amount of each one in order to determine mathematically or osteochemically which one is the limiting factor or which one is the reactant in excess. Thank you for listening. I hope that you enjoy this lecture. We come back again to the 45 minutes lecture or period. It is quite enough, and I think we spent good time together. I hope you enjoy it. Thank you and have a good day.